Okay, Assalamualaikum and good day to everyone. Today we will continue with chapter 6, junction field effect transistor. So in this chapter, there will be two sub-chapter, which is JFET and also MESFET. So the JFET concept can be discussed as follows. So JFET has three terminal semiconductor device. So JFET is basically function as a switch or resistor, and is also usually used to build amplifiers. So the JFET phenomena was first patented in 1920s, and the first building construct can be explained as in the figure below. So based on this figure, ABC represents the terminal semiconductor devices. A voltage applied to the metal plate, which is the aluminium, can modulate the conductance of the semiconductor under the metal. And also the voltage applied can control the current between the ohmic contacts, which is between metal and also semiconductor. So good semiconductor materials and processing technology were not available during that time. It was not really popular and not seriously considered until 1950. So the theory of modulate the conductance of a semiconductor by electric field that is applied perpendicular to the surface of a semiconductor, we call it as field effect. So this is applied also in MOSFET. Okay, so this type of transistor, which is JFET, is also known as unipolar transistor because it emphasizes only one type of carrier. That's why it was called uni, only consider one type of carrier, which is the majority carrier. So we know that for NJFET, okay, the hero here is the electron, while for PJFET, okay, the one that is really affect the system or the operation is the holes. So this figure represents the JFET symbol in circuit. Okay, there are two types of JFET, which is N-channel JFET and P-channel JFET. So at the symbol, there are three important terminals, which is gate, source, and drain. Same goes to P-channel JFET that has gate here, drain, and also source. So the difference between the N-channel JFET and P-channel JFET not only based on the position of source and drain, but also the arrow pointed at the gate terminal. Okay, so for the N-channel JFET, the gate terminal has a point in arrow, while for the P-channel JFET, it has a point out arrow. Okay, now we take a look on the circuit for each type of JFET. For the N-channel JFET, the channel will use N-type substrate. Okay, so there are P-type materials. Okay, there are P-type material at both sides of the channel. Both sides of channel that make a PN junction. Okay, so same goes to the P-type JFET. So in P-type JFET, P-type material or P-type substrate is used as the channel. So at both sides of the P-type material, there are N-type material that will be operated as a PN junction, which means the PN junction will be formed at this area, all right, between this channel. The depletion region will be happen here, somewhere inside the channel. So the channel will be connected between source and drain terminal at which the current is flow. So now we study about the basic PN junction operation. So this is the cross section of a symmetrical N-channel PN junction FET. Alright, so this is N-channel. So the N region between the two P region is known as channel. Okay, this part is known as channel. The majority carrier electrons flow between the source and the drain terminals. So the source is the terminal from which carriers enter the channel from the external circuit. Okay, in case there is the voltage applied here on the gate, so the carrier will enter the channel, okay, from source to drain. So the drain is the terminal where the carriers will be leave, okay, or drain from the device. So the gate is one that is control the terminal. So gate play a main function to control the terminal. So the two gates are tied together to form a single gate connection. You can see here, both P substrate here is connected, okay, is connected via one single gate connection. Alright, since majority carrier electrons are involved in the conduction in this n-channel transistor, electrons is now a majority carrier device. So n-JFET is also known as a electron majority carrier device. So in case for p-channel JFET, the reverse operation is expected, in which the region of P and N will be opposite, alright, and the current direction as well as the voltage polarity will be also in opposite directions. Okay, basically PN junction JFET, for P FET, okay, lower frequency is expected due to the lower hole mobility. Now we move for IV characteristic for small VDS values in terms of varied VGS value. Okay, first we consider VGS is equal to 0. Okay, so the channel here is N channel. Okay, so there is a p-type substrates that attach between two channels that attach also with the gate terminals. Okay, now let's say if the source is at ground potential and small positive VDS is applied to the NJFET, a drain current is produced between the source and the drain terminals. So N channel is basically a resistance, right? So the resistance. So in terms of there is no, or the resistance is small here. Okay, so I versus VDS is approximately linear, in which we can consider it is I equal to V over R. Okay, so I is directly proportional with the V, and the graph is become linear when VGS is equal to 0. Now, what if we apply a small reverse bias voltage on the gate? Okay, so when the reverse apply bias voltage, it is applied to the P type substrate here. So based on the PN junction theories, when negative voltage is applied to the p-type substrate, okay, what happened on the PN junction is the holes in the p-type materials, the majority holes in p-type materials will be attracted towards the negative electrode, which makes the space charge region become widened. Okay, when the space charge region is become widened, okay, the channel region now is become narrow. So when it is narrow, the resistance of the N channel is increasing. There is less of the ability for the current to flow. So in this case, the curve of IV is become decreasing. The curve of ID is become decreasing. So when we apply a larger value of reverse bias voltage to the gate, okay, so now the hole at the p-type substrate that attached to the gate will now more attracted to the negative terminals. Until then, it will be maximized at a certain point that both sides of the p-type substrate is meet together. Okay, when it meets together and it completely fill the n-channel region here, we call it as a pinch-off conditions. Okay, we call it as a pinch-off condition. When the depletion or when the channel is completely filled, so resistance is high or to the maximums or infinity, in which there will be no current are able to be flow. So based on the IVDS curve, we can see here that when the pinch-off condition is achieved, the current is equal to 0. In case of VGS is equal to 0 and the drain voltage is changes, alright, when VDS is applied to the n-channel region based on the PN junction theories, okay, if positive terminal is applied to the n region, so the reverse bias condition will be applied. When reverse bias condition applied, the electron as a majority carrier in the n-channel region will be attracted towards the terminal, towards the positive terminal, and make the space charge region to be increasing. So in this case, when VDS is further increased, the space charge region at the end or nearby the terminal will be increased. So when this condition is happen, the resistance here is increased and the conductance at the end of or nearby the terminal will be decreasing, so that the current will also be decrease. Okay, the IV characteristic will be also decreasing, right? So now we increase a larger value of VDS. When we increase furthermore the VDS value, the space charge region will be also increased at both sides of the PN junction and meet at the end of the terminal of the drain source of the drain. Okay, so this when this is happening, okay, there will be no current can be flow due to the pinch off here. Okay, the pinch off is happen here, and at this particular point we refer it as a VDS saturation point, in which ID will not be increasing, so it will be constant, the constant. Okay, it will not be decreasing, but it will be constant. Okay, at this particular point we call that the VDS is achieved the maximum value and normally known as VDS sat or VDS saturated point, saturation. Okay, so when VDS is larger than VDS sat, the transistor is said to be in saturation region, and the drain current, okay, is not depends now on the VDS value. So at first glance, we might expect that the drain current is going to be 0, but we will show why this is not going to be happen. So now, in case of VDS is larger than VDS sat, okay, so here is VDS saturated. So now this is ID. So we want to discuss what is happening here is because of the delta L here, at which the pinch off condition is achieved, the delta L at which the space charge region is meet together. If delta L is less than L, L is represents the length of P substrate. Okay. Now, if delta L is less than L, the electric field in the n-channel region is constant. Okay, and the drain current will also constant. So what makes it still have a current is that because the electrons that move to the n channel can be injected into the space charge region, and due to the electric field force, it could be swept through the drain contact area. So once the carriers are reach the drain region, the drain current will now not be depends on the VDS anymore. So ID will not depends on the VDS, and the current now is become constant. So the second type of JFET, we call it as a MESFET. So the basic MESFET operation can be explained by refer to the cross-section of the N-channel MESFET with a semi-insulating substrate here, which is gallium arsenide. So gallium arsenide here is used as the active region, and it has a very high resistivity material and referred to as a semi-insulating substrate. Okay, so what is the difference between JFET and MESFET is now the gate is connected to the rectifying contact, or we call it as a Schottky barrier rectifying contact. Okay, so to enable a current flow, okay, the depletion region at the N channel here must be very, very narrow. So to explain this, okay, we must understand that there is a potential barrier, okay, between the metal, semiconductor, and also semi-insulating substrate. Okay, so we must control, okay, adjust what is the voltage applied here, okay, what is the voltage of the VGS that enable the current to flow from source to drain, oh sorry, from drain to source to drain. All right. So a little bit information about the Schottky barrier diode. This diode does not use a PN junction, but a junction with a type of metal on one side and an N-type semiconductor on the other side. Okay, this type of junction is called a Schottky junction. Okay, so for the forward bias, to make it a forward bias, the negative terminal is connected to the semiconductor N-type substrate, while the positive terminal is applied to the gate. Okay, so in terms of reverse bias, positive terminal is applied to the N-type substrate, while negative terminal is applied to the metal gate here. So in case for reverse bias, the depletion layer will be formed. Alright, because the positive terminal, so the electron will be attracted, go to the positive electrode and make it less, then the depletion region or depletion layer will be formed between the Schottky junction side. Alright. So a reverse bias gate to source voltage in which negative VGS is applied to the MESFET. Okay, a space charge region will be formed and modulates the channel conductance. So in this case, the N-channel conductance will be decreased because the resistance is increasing. So when the resistance is increased, and if we apply the negative gate voltage at a large value, we will achieve the pinch off condition similar to what we expected as in a JFET operation. Well, the arrangement of MESFET, okay, the arrangement of MESFET, which is like this, can also be known as N-channel enhancement type MESFET. Okay, so this can be referred back to the MOSFET operation. Yeah. Okay, so the MESFET, we can say it is pinch off at VGS is equal to 0, and for the zero bias voltage applied to the gate, there are potential barrier between the channel and also the substrate, and also there is a potential barrier between channel and also the metal. So the majority carrier electrons are confined in the channel region. So in terms of equations, the built-in potential barrier is equal to Vbn minus Vn, in which Vn here is referred to potential or potential barrier in the semiconductor, which is equal to Vt ln Nc over Nd. Okay, so VBI here is equal also to KT over E ln NAND over NI square equal to VT ln NAND over NI square. So this VT is the thermal voltage, while VT here is equal to threshold voltage, right? So to open a channel which enable the flow of current from source to drain, the depletion region must be reduced. So a forward bias voltage must be applied to the gate. So when a forward bias voltage is applied, the depletion region will be just extend through the channel, and this condition we known as threshold condition, which is VGS is equal to VT when the depletion region is just at a junction between the semi-insulating substrate and also the channel. Okay, so the threshold voltage is the gate to source voltage that must be applied to create the pinch-off condition. That's what is called a threshold voltage. For N channel, the MESFET is positive. The voltage is positive in contrast to the negative voltage for the N channel depletion mode devices. So if we apply a larger forward bias, the channel region will be open. So in this case, the depletion region will be decreased. The depletion region will be decreased. Okay, so enable a current to flow, okay, between source and also the drain. So the device now is known as N-channel enhancement mode MOSFET. Okay, now we see how to calculate the internal pinch of voltage, and drain to source saturation voltage. So first we need to understand several terms used in the equation. Alright, so there is a symbol A, which is the metallurgical channel thickness. It is a location between the P gate region and the substrate. So A is referred to the metallurgical channel thickness. Okay, besides A, there is also H. So H is represent the induced depletion region width for one side. So assume that drain to source voltage is 0, VD is equal to 0. So H is equal to 2 times permittivity in bracket VBI, built-in potential barrier, minus with the value of VGS divided by electrons value times with donor concentration. Okay, donor concentration of the donor atoms. So in bracket to the power of half, or third answer. Right. So now at pinch off, which is H is equal to 0, the total potential across PN junction is called the internal pinch off voltage and denoted by VPO. So VPO is equal to E times S squared times ND divided by 2 epsilon S. So the internal pinch off voltage VPO is not referred to the VGS. Alright, so the gate to source voltage that must be applied to achieve pinch off is described as the pinch off voltage, and is also variously called as the turn off voltage or threshold voltage. So VP, or pinch off voltage, is equal to VBI minus with VPO. So in terms of MESFET operation, okay, pinch off voltage is known as a threshold voltage. So threshold voltage is equal also to VBI minus VPO. So assume that the PN junction of a uniform doped silicon N channel JFET at T equal to 300K has doping concentration of Na and Nd. So assume that metallurgical channel thickness is 0.75, which is equal to 0.75 times 10 to the power negative 4 centimeter. Remember, unit is very important. So calculate the internal pinch of voltage, which is VPO, and pinch of voltage, which will be VP of an N channel JFET. Okay, to find VPO, we just use this equation and substitute the value and we got the answer. So to find pinch of voltage, we need to find first what is the VBI. So VBI is equal to VT ln NA over ND divided by NI square. So once we got VBI, then we can get the answer of the pinch of voltage. So if you need to solve a problem based on P channel BN JFET, so the formula will become H is equal to 2 times epsilon in bracket VBI plus VGS divided by electrons times with the NA in bracket half. So what the difference here is the sign of VBI plus VGS and also the NA here. Okay, just now for N channel PN JFET, it is VBI minus VGS and END. So beware with the equation that you are going to be used. Yeah. So again for P channel JFET, okay, the internal pinch of voltage will be equal to E times S square times with NA divided by 2 epsilon S. So same goes to the pinch of voltage. Okay, they will be opposite formula in which VP is equal to VPO minus with VBI. The problems. Okay, now let's restart from below. Okay, why? Because to find A, we need to use these equations. Alright, to find A, we need to use this equation here. Okay, but to use this equation, we need to find what is the value of VPO because this is what is the missing value here. So to find VPO, okay, we need to use this equation, which is VBI minus VT. So we know that VT is being given, which is positive 0.25 volt. But what is the VBI? So VBI could be found by using this equation, which is equal to VBN minus Vn. Okay, they have given the value of VBN, which is equal to 0.89. So now we can find Vn from this equation, which is Vt ln Nc over Nd. Okay, so once we find the missing value here, okay, with Vn, then we find what is the VPO, then we can get the channel thickness value here. Okay.